Humans have powerful visual recognition abilities that enables us to perform complex image understanding tasks. However, attaining expertise in challenging visual domains can be a long process, requiring large amounts of training. In this work, we address the problem of teaching visual categories to human learners. Specifically, we propose a novel machine teaching algorithm that takes a set of labeled images as input and by modeling noisy learners, generates a sequence of teaching images. There's a large body of work exploring the design and analysis of algorithms for automatic teaching, starting with theoretical models with limited noise assumptions to models that take into account the memory decay during learning. Approaches exist for teaching visual categories, but they typically provide very limited feedback to the students during teaching. Specifically, existing approaches typically perform the following two steps. First, they show an image to the student and ask them to guess which category it contains. Then they provide feedback in the form of the correct class name. Crucially, it's up to the student to determine which visual features or attributes are discriminative for that class. This can be very challenging to discover for fine-grained visual categories. Feedback is much more informative when it comes with some form of explanation. Our teaching algorithm provides visual explanations as feedback and models how easy these explanations are for students to interpret. Here, I'll present some intuition as to how our model works. As input, it takes a low-dimensional embedding of a set of images, displayed here as a set of 2D circles, where the color indicates the class label. We also require corresponding visual explanations, highlighting informative regions for each specific instance. Note that not all explanations are equally informative, and our teaching model takes this into account when selecting examples. Finally, we also assume that we have access to a set of hypotheses that represent different schools of thought that may be held by the students. Here we display these hypotheses as linear classifiers, where H star represents the hypothesis we wish to teach. For details on how we can automatically generate this information, please consult our paper. Our probabilistic model selects teaching examples along with their corresponding explanations so that hypotheses that are inconsistent with the ground truth are eliminated as quickly as possible. When each teaching example is displayed to the student, shown here in orange, we model them as switching to another hypothesis if it's inconsistent with the information they've just received. The thickness of the lines represent the posterior probability associated with each hypothesis, also shown in the top right corner. This process then repeats until a set of teaching examples has been selected that eliminates all inconsistent hypotheses. We performed experiments on real human learners across 3 different datasets using Mechanical Turk. Our datasets included images of butterflies captured by citizen scientists, where we see representative images on top with their corresponding explanations below. Images of human retinas connected and labeled by ophthalmologists, and handwritten Chinese characters. For our experiments, participants first performed a brief tutorial to familiarize themselves with the teaching interface. Then they were shown a sequence of teaching images, and for each image they were asked which category it belonged to. Feedback was given in the form of the correct class label along with a visual explanation. After teaching, they were evaluated on a held-out test set. We compared our model against several baseline teaching algorithms. On the left, we show the test time performance of students who were taught with random images with no explanations. Here students are binned based on test performance, and in this example, we see that while most perform better than chance, they're not very good overall. In comparison, our model significantly improves the generalization performance of students. For more details on results, please consult our paper. Thanks.